today my talk will be based on a part of my PhD thesis. The title is Mainshock and Aftershock sequence simulations in a nonplanar fault network. So let's start. Oh, do you see the screen right? Correctly? Okay.
Yes.
Yeah, thanks. So sorry. Okay, let's start. So I'm interested in how aftershocks occur and its physical mechanisms. So if you look at the good high resolution aftershock catalogs, aftershock generally, its distribution generally delineate fault planes on the underground. I'm showing two examples of the recent earthquakes, not very recent. So that 2000 Western Totori earthquake and 2019 Ridgecrest California earthquakes. So you can clearly see the fault planes from the aftershock distributions. And actually this high resolution aftershock map are used to estimate fault planes. But actually, majority of aftershocks are of fault events. There are some reasons to argue that. So one is from Yuktaki and Yu 2017. They say that even if observational error is taken into account, aftershock width is larger than typical fault zone width. And also they say that many focal mechanisms are inconsistent with the Mainshock fault plane. They are too diverse, like this figure. And also, from the Ridgecrest earthquakes, aftershock distribution shows clear conjugate planes, which is crossing the main fault. This is another reason why many aftershocks are fault events. However, if you think of physics, this aftershock distribution can be unexpected because from Coulomb stress perspectives, aftershocks should be concentrated at the edge of the slipped fault, where stress concentration is happening. And on the fault, stress, it should be stress shadow. So this, however, this paradoxical situation maybe coming from the oversimplification of natural fault geometry. So natural faults are neither flat and isolated. So many field study, geological studies are documenting that natural fault can be described as a self-affine fractal concept. They are nonplanar at all spatial scales. Also, natural fault, major fault usually have damage zones on its surrounding, and the damage zones contain numerous subsidiary faults. And if you consider the effect of natural fault roughness, complex geometry, you can reach the conclusion that slip on a fault gives heterogeneous stress near the fault, like this plot. So if there's a slip on this fault, many places are actually stress shadows, but some places are not a stress shadow. The Coulomb stress is increasing after the earthquake. So we can make an hypothesis for earthquakes, which is happening at conventional stress shadows. The hypothesis is that stress heterogeneity coming from the fault roughness causes aftershocks on damage zone subsidiary faults, which is located at apparent stress shadow. So this hypothesis is not very novel. It's not my novel idea because many people are already thinking about that. So here, my purpose is that putting this hypothesis into physics-based numerical simulation of earthquake sequence, which is the topic of this seminar series. So my problem setting is as follows. The fault geometry is like this plot. The long red line is the main fault. This has fractal geometry with aspect ratio being 0.01. And the Mainshock rupture is artificially initiated by putting a stress perturbation at the center. This main fault is surrounded by many 600 subsidiary faults. And they are 0.6 kilometer in length. And their orientation is completely random. And other settings are like follows. All the fault elements are governed by the latent state friction law with aging type evolution law. And all the elements are velocity weakening. And the initial stresses on the fault are resolved from the spatial uniform stress tensor, which is sigma 1 makes 30 degrees against overall faultless x-axis. From this calculation, the initial shear over normal stress and initial slip rate is a unique function of fault slope. Oh, I forgot to state that the initial state variable is fixed. So this leads to this initial slip rate and initial stress distributions. And the important thing is that this simulation is single Mainshock and aftershock sequence simulation. And because I don't have external loading, time-dependent loading, so I cannot do multiple cycle simulations. Of course, it's gonna be interesting, but for how to say, as a first work, I only focus on single Mainshock and aftershock simulations and putting multiple cycle simulation in future work. And a little bit about my computational code. I want to talk about a little bit about my computational code, which is HBI. So I have been developing this code for over 5 years. This is quasi-dynamic 2D and 3D earthquake cycle simulation code using boundary element method, and that is applicable to general fault geometry, like nonplanar faults or many fault networks, so which is suited to this work. And for efficient computation, the code is accelerated by H-matrices method. This is quite a popular method recently, so many people working on this topic are using this technique. And my code is open source, so you can take a look at my machine source code from this website. And my code is HPC oriented, so that means it works quite well in a supercomputer system using like tens of thousands, many CPUs. And my code is already validated with C's benchmark problems in SCAC, like these papers. So let's move on to the result. First, I'm showing the maximum slip rate evolution using this aforementioned fault geometry and initial conditions. So first, if you look at this red line, which is showing the maximum slip rate of the main fault, the main shock happened, and its duration is around 50 seconds. And the main shock ruptures the entire main fault. It's not partial rupture. So actually, it was adjusted by initial stress. So if initial stress is smaller, the main shock cannot rupture the overall all the fault trace. It's partial rupture. So, but I'm mainly looking at the full rupture regime for simplicity. And after the main shock terminated, the red line is decaying over time. So this means there's no aftershock on the main fault. And if you look at the green line, which is subsidiary faults, for subsidiary faults, it's showing many spikes after the main shock is finished, completed. So each spike corresponds to each aftershock happening at some subsidiary small faults. And so I actually run many ensemble of simulations, but usually the number of subsidiary faults that produce aftershocks is like 10 or 20 out of 600 subsidiary faults for this geometry. So majority of subsidiary faults cannot produce aftershock, actually. And if you look at more closely on a subsidiary fault that produced aftershock, this is showing the evolution of slip rate and friction coefficient shear over normal stress over subsidiary fault. So if you look at this, so during the main shock rupture, there is a sharp increase of stress and also slip rate. This is caused by the passage of the rupture front of the main shock. And then gradual increase of stress is caused by the static slip of the main shock. And then main shock is completed, and this subsidiary fault enters the nucleation phase. And within a finite time, it goes to instability and producing aftershock, and stress drop is happening. So I think one interesting thing in this plot is the effect of the passage of the rupture front. And in this case, it's the effect of the passage of the rupture front is not large enough to instantly cause kind of aftershock. But if this is much larger, the fault would produce co-seismic fault damage. And this is showing so here I'm focusing on the statistical properties of our aftershock simulation. So to do so, I'm doing many ensemble simulations and plotting the result of many ensemble simulations in a single figure like this. So the black dots are the location of the subsidiary faults that produced aftershocks. And the color is the delta CFF, delta Coulomb failure function, calculated for optimally oriented fault, and also from the main shock slip distributions. So they are agreeing each other. I mean, aftershock locations are locally elevated CFF. And actually it's often corresponding to releasing bend, where normal stress are decreased due to slip. And if normal stress is decreased, the Coulomb stress is increasing. And if you look at the distribution of the aftershock, all aftershocks are within 1 kilometer or something from the main fault trace. This is because this pattern, I mean, the finite width of the aftershock is coming from the spatial pattern of the stress perturbation from rough fault slip, because the stress perturbation from fault roughness decays with fault normal distance from the Mainshock fault. So the stress heterogeneity has to be large enough to overcome the overall stress shadow effect. This causes the finite width of the aftershock distribution. And I think so I want to focus on this plot, which is main fault roughness, which is comparing the effect of the main fault roughness. So alpha is the parameter of the main fault roughness. So alpha equals 0.01 is a 1% roughness. And if the main fault is completely flat, there's no aftershock. There's no aftershock on the how to say side of the fault, and all aftershocks is concentrated around the tips of the fault. But as increasing the roughness of the main fault, the number of tip aftershocks decrease, and the number of wall aftershocks, fault side aftershocks increase. And this aftershock distribution is more natural. I mean, similar to what we are observing in nature. So I think, so this suggests that the fault roughness is plays a very important role in controlling the aftershock distribution. So let's move on to the temporal behavior of aftershock seismicity. So we all know that aftershocks universally obeys the power law time decay, which is called Omori-Utsu law. And our simulation clearly reproduce the Omori-Utsu law. So here I'm showing the temporal decay of aftershock seismicity from the ensemble, our simulation ensemble. And the left panel is showing the effect of initial state variable. And the right panel is showing the effect of initial stress. So initial state variable seems to affect the duration of the aftershock, and initial stress seems to affect the productivity of aftershocks. So actually, it's not surprising to get Omori's law, because so we are using a latent state friction law, and in the oral paper by Dietrich 1994, he showed that Omori's law can be derived from fault populations obeying latent state friction laws. But his paper has many assumptions. Of course, it's analytical derivation, like such as interaction. There is no interaction between sources, or faults are considered to be a spring slider, which doesn't have any finite size. And also, in computing time to instability, the original paper have to assume well above steady state in the sense of latent state friction. But I think this assumption is not essential, and the Omori law is a very, very robust property for how to say, for fault population that obeying latent state friction against some stress perturbation like Mainshock rupture. But So the last point is important, I think. So in all our simulations, the duration of aftershock is finite, and there is no seismicity after the end of the aftershock. This may be because we don't add any external loading, time-dependent loading in our model. So this is why I'm interested in what happens if I do earthquake cycle simulation with this fault geometry with some proper external loading system. But I think there are many ways to add loading to this type of complex fault systems. So next, I'm talking about aftershock migration. So from observations, many earthquakes shows temporal increase of the expansion of the aftershock area. This is extreme natural example from Noto Hanto Japanese earthquake. So in this case, the aftershock expansion is very rapid and the final aftershock zone is much larger than the Mainshock fault. And my simulation also reproduce aftershock migration like this plot. And the simulation shows logarithm time expansion. This is also consistent with many observations. Also, the how to say migration distance is smaller than this observation. And this extension can be understood from physical perspective that so as we go away from the fault edge, the stress concentration, stress increase from the main shock is getting smaller. This is from the famous square root singularity of stress concentration from fracture mechanics. And from latency friction, the lower stress means longer time to instability. So this apparent diffusion is just reflecting the difference of time to instability and which is coming from the difference of stress, perturbed stress from the main shock. And we can, with some assumption, we can get analytical solution for this. And the important thing is that there's no afterslip, actually more precisely, no velocity strengthening creep because all the fault is velocity weakening in my model. And also we don't have fluid. So that means migration of aftershocks does not necessarily mean a seismic slip or fluid diffusion. And this is the last topic, which is focal mechanism statistics. So because I put 600 differently oriented fault, subsidiary fault. So I can do statistics for focal mechanism of aftershocks. And this is showing the histogram of focal mechanism of aftershocks. And you can see its bimodal distribution. And the two peaks correspond to the optimal planes against the background stress field I pressed like this. And if you do the same simulation, but with smaller friction coefficient and also initial background stress, we get this histogram, which is showing much diversity in focal mechanism. So this is coming from the weak fault shows more stress rotation from the same stress change, stress perturbation, which is reasonable. And it is reasonable, but this result might suggest that the scattering of focal mechanism is an indicator of the absolute stress strength on the crust. But maybe many people are thinking the same thing. So this is a summary of my research. So I think this is one of the first earthquake sequence simulation showing the many different spatial temporal characteristics of aftershocks. And in my model, aftershocks are ruptures or small subsidiary faults located in the fault damage zone. And as you see before, fault roughness is necessary to explain aftershocks distribution delineating Mainshock fault. And if you look at the temporal decay, the Omori-Utsu law is a universally reproduced. So which is a robust property for fault populations with latent state friction and external stress perturbation. And finally, diverse focal mechanism of aftershocks is observed for weak faults. So this is my all the things that I want to talk. So thanks for listening. I hope you enjoyed.